Hello, my name is Tumbajana and I'm going to take you through uh, VL learning and Q learning in machine learning. So I'm Tumbajana once again, and let's start with Q learning. So Q learning is a model-free reinforcement learning, and this algorithm is used to teach an agent how to act in an environment by learning the best actions, like the best and good actions to take in different situations or states. So this model free reinforcement learning algorithm it learns an action value function, or we call it the Q function, which represents the expected cumulative reward for taking a specific action in a specific state. So we have our equation here, which is Q brackets SA, and which is equals to QSA plus alpha into R plus gamma max of Q S prime A prime minus Q into S A. So I'm going to break down this equation step by step. So S represents the state, like the current situation or condition that like the agent is in. Let's say for example, you have like in a video game, like the state that could present the position of the player or the state the player is in. And you have A, which represents the action, like a choice or decision the agent can make in a given state. So let's say in a game, the player takes the action of moving it to the left or the right, or like to jump. Then R, like R stands for the reward, or like the feedback the agent receives for taking an action in that state. So, for example, a positive reward, uh, like positive rewards encourage good actions, while the negative rewards they discourage or encourage bad actions. So Q, these are like the Q value, and this Q value we have the state and the action. So this is what Q learning tries to learn, and it estimates like how good it is to take action. Action A is action A in a state S. So the higher the Q value and the better the action. So for example, so let's continue. The current state, so the Q with S and A, that is the current state or like the existing knowledge of how good it is to take action in that state S. Sorry, let's go back. And so when this alpha, that alpha, it controls how much the Q value is updated, like a value between 0 and 1. When the alpha value is low, that means there's a small update or like slow learning. And when it is high, there is a large update, like there is a large update, and there is a faster learning. And R stands for the reward, like I explained before. So this immediate reward for taking action A in the state S. And we have gamma, and this one is like the discount factor. So this discount factor it determines the importance of the future rewards, a value between 0 and 1. And when it is high, there is a focus on long-term rewards, and when it is low, there's focus on short-term rewards. And lastly, we have the max Q, S prime, A prime. So this is like the basic Q value for the next state S prime. This represents the estimated like future reward, like for taking that action or the best action, this S prime. Basically, what it does, this equation it updates the Q value by comparing the current state to a new state based on the reward and the future based action. That's how it can be able to predict correctly using Q learning. And continuing to Q learning steps or like the algorithm steps. So basically, this Q-learning is relatively like straightforward, straightforward compared to many other reinforcement learning algorithms. So it doesn't require even complex models or deep learning initially, but the main task is to maintain an updated Q table. This it starts by initializing the Q values. It chooses an action for which it has to take. Then after taking that action, it observes the reward and the next state. Thereafter, it updates the Q values in the Q table for the previous state action pair. Then it repeats until there is convergence, or like until the model achieves the state it wants to achieve. And yeah, so this algorithm, so basically it makes a good starting point for beginners in RL, and for a problem with small state action spaces. Let's go forward to the Q-learning implementation. So basically here we are going to discuss a table. An example, we have this table. So this works with a simple Q table and applies a straightforward approach rule. And we have our parameters. And so we are going to start by initializing the Q table with the states, which we have 10, the actions as 2, and so here I have the components, which are the two-dimensional arrays of shape. We have states and actions. So going further to the parameters, we have the alpha, which is the learning rate, as 0.1. Have the gamma, the discount rate as 0.9. Have the epsilon, the exploration rate as 0.1. So go forward to the loop, which will implement the iterations for the Q values. So we have and so here we have, so let's start with for episode in range 100 state. So we'll iterate the states, and for each step in that range we'll choose the action using the epsilon greedy, and also in that loop we have the if function. So and here we can compare the action and according to that state. So and here you can simulate like the environment response, so that you can get the reward and know the next state. And sorry. And so going downwards, the Q-learning update rule as below. So there it calculates the state and the action. So going forward to the advantages of Q-learning, I'll start with this the first one. So this Q-learning algorithm is simple to implement, and it is relatively straightforward to code compared to like the many other reinforcement algorithms, and it does not even require complex models or deep learning initially, like I explained before. The main task is to maintain like the an updated Q table, and it makes it a good starting point for beginners, like how I explained before. So going forward to how this model is free, it doesn't even require a model of like the environment. So it is a free model, and this means like it doesn't need a complete understanding of how the environment works. And this model can predict what the next state and the reward will be given to the current state and action through the equation that I explained above. And in a complex environment, like building an accurate model can be a very hard or even like impossible. But it directly learns from experience, like without trying like to predict the future states, but it makes it more practical for the real world problems, like the way it handles the situations. And it also uh, like the proven converges under certain conditions. That this means that with enough training, the Q-learning will find the optimal policy, the best possible like way to act in every state to maximize the rewards. And this is very important. Like this mathematical guarantee gives the confidence through this that the mathematical equation that Q-learning will eventually solve the problem as long as the conditions are met. So, like in the practical convergence, it may take a long time for a large state space, but the guarantee is still there. It is assured to happen. Going further to the limits. So it is limited, like it struggles with continuous action spaces. So but whereby it works well in the like discrete action spaces, like going to the right, to the left, like moving to different directions. But continuous action spaces, when the actions are like continuous, let's say for example, like scrolling, the speed, or the angle of a robot arm, it becomes almost impossible to maintain a Q table like for every action. And the table would need infinite like entries to represent all possible actions which would be taken. And this seems very like impractical or even impossible. And there's a high computational cost for large action spaces, whereby even with discrete actions, Q learning struggles if there are too many states and actions. So the basically the Q table grows exponentially as the state action like space increases. So let's say uh, high memory usage and low computational time, like computational times, and these are things that impact this cost. And going further to another limitation, so this requires careful tuning of exploration, whereby it relies on a balance between exploration and exploitation, and whereby exploration strategy, or like we call it the e-greedy, it's often used in the Q-learning where the agent randomly explores with probability and exploits the probability. And going next to the V-learning. So V-learning is basically the value advantage learning. And this learning is an extension of traditional Q-learning. It's like and its main goal is like to improve learning efficiency by splitting the Q value into two like components. And as the equation is, we have the Q value, which is the Q, where I have the state and the action. So the total like expected reward for taking action in A and in state S, that is the Q. And the value function, that is the V, whereby the expected reward for being in the state S, that's how we represent it as VA brackets S. So regardless of which action you take, it tells you how good the state itself is. And lastly, you have whereby we add on A, which is the advantage function. So this advantage action, it measures like the advantage of taking an action compared to the average action in that state S. So a high advantage means like the action is better than the other in that state. So continuing to the algorithm of this value advantage learning. So we begin by estimating the value function. So this value function, like the value of the current traffic situation, how it is to be in that state. Then after it estimates the advantage function, which is A. So this advantage of like turning left versus going to straight or forward in any directions, like if turning left leads to a much shorter route, it will have like a high advantage. Then after it combines them to like approximate values. Then after it uses in the reinforcement learning updates for better policy evaluation. And here we have an example where there's a dueling of DQN example. So, and we use a new like a neural network to separate the value and advantage components by splitting the Q function into value and advantage, improving so this therefore improves learning efficiency. So going further to explaining how this code is, I'll have libraries that have imported, and this dueling DQN, we call it the DeepQ network. So we use a neural network to compute key values by separating them into like the value function and advantage function. So, and here we train the loop into the dueling. So you have the classes, and in those classes you have the functions. So the examples of this loop we have here. The example, we have the state space dimension and the action space dimension, which we use to estimate. And we have the main training step with the sample state and target Q values here. We use the neural network based, like the deep learning, and also we forward the pass through a neural network, and so that we can have a more stable and efficient like for complex environments. So we should have the efficient and more stable models for complex environments. And this also reduces like the variance and improves the learning efficiency. So basically in this value advantage learning, we calculate the advantage of which route we should take so that we can predict well. So, and among the advantages of this value advantage learning, it handles continuous state spaces, efficient for large state spaces, and also improves like sample efficiency in deep learning, deep reinforcement learning. So we have comparisons here, like according to the feature Q learning, Q learning directly aligned due to the action value it is directly aligned, while in V learning it is decomposed into V, the value and advantage. And according to efficiency, Q learning is good for small spaces, while VA learning is better for large spaces. And convergence speed, Q learning is a bit slower, but VA learning is faster. And according to stability, Q learning can be unstable as VA learning is more stable. And according to complexity, VA learning is not even complex. It's a non-complex model. Whereby its complexity is lower, and VA learning, its complexity is a bit high. Therefore, I'll finish with the limits of value advantage learning, whereby computationally it's more expensive than VA learning. Q learning. It also requires careful tuning of like value and advantage estimations. It can be unstable, so on. And lastly, more complex to implement than Q-learning. Thank you.
My name is Nabawanga Afwa, and I'm going to take you through the real-world applications of Q-learning. To start with, Q-learning is applied in game playing. That's the likes of AlphaGo, Chess AI. Okay, basically, Q-learning is used in AI agents to learn optimal strategies in various games. So for the various games I'm talking about AlphaGo, whereby these AI systems use reinforcement learning concepts such as Q-learning to go ahead and master complex games such as chess. Then basically they do this by playing against each other over and over again. So for robotics control, Q-learning, basically it is used for decision making and control tasks. That's why it's called robotics control. To give an example of self-balancing robots such as the Boston Dynamic robots, they go ahead and be able to learn how to maintain balance and work smoothly through Q-learning. Then recommendation systems. The the Q-learning concept, it's applied in recommendations engines to personalize user experiences. Give an example of e-commerce. E-commerce on platforms such as Amazon, Alibaba, Q-learning optimizes product recommendations based on browsing, the purchasing behavior, thus improving on the conversion rates. To continue with the real world applications of VA learning, remember, it works with continuous state spaces, then it can work on large states. So basically, it's applied in continuous control problems. When I talk about continuous control problems, look at environments where the actions and states are continuous. To give an example, are the drones. These drones which are used maybe on ceremonies to capture what's going on. So those drones, so Q-learning enables them to go ahead and learn smooth and energy efficient flight paths and in dynamic environments, resulting into low battery consumption. Then for financial modeling, VA learning is remember okay, the basics of VA learning. We have first of all, it can handle complexity, then high dimensional data. Look at those large data and continuous. So basically, due to those characteristics or what it can handle, so it can go ahead and be applied in financial modeling. The likes of businesses, e-commerce, yeah. Then for large scale state spaces, basically eagle weather prediction. Just like we said, it handles continuous control problems. So when we come to weather prediction, remember weather can't be stable. It changes in terms of maybe humidity. Look at temperature. Look at the wind speed. So basically, V-learning goes ahead and ensures efficient casting. Yeah, efficient forecasting that's being used in weather prediction. So when to use Q-learning and when to use VA learning. When to use Q-learning? Q-learning it's basically used in environments with discrete actions. Why environments with discrete actions? Remember, if discrete basically, okay, in simple terms, it means the number of states is small or manageable. So, and basically Q-learning can work on such concepts whereby the number of states, if it's small or manageable, yeah, Q-learning can go ahead and use it. So you can go ahead and use Q-learning for small and manageable states. So it can be used in environments with discrete actions, in model-free environments. When I talk of model-free environments, I mean environments whereby the dynamics are unknown. Like if the dynamics are unknown, then yeah, we're okay to use Q-learning. Then for scenarios requiring action value estimation, remember in Q-learning, we basically focus on small and discrete actions. So the moment we have the action, remember it's small, so we can go ahead and manage scenarios which are action value, which is not the case in VA learning, where we need to manage actions which are in V learning, where we need to manage actions which requires the state value. At the other time, in Q learning, we require just the action value. Then where to use the VA learning in environments with large state spaces. When you talk about the large state spaces, look at instances whereby the number of states is too large. Remember, for Q learning, it was small, but for this time around, we look at states whereby they are large, so we apply VA learning. Then model-based or model-free environments, we can also use VA learning in model-free environments. Then for scenarios which require state value estimation, we can go ahead and use VA learning. Some of these scenarios, look at a scenario whereby traffic. Okay, let me give an example of traffic. So in traffic management, a model goes ahead to detect whether like the traffic is congested or whether the flow is really smooth, like there is no traffic or it's congested. Yeah, so to continue on the algorithm comparison, to compare the algorithm of Q learning and VA learning. Remember, basically, Q learning focuses on action selection. Yet, just like we've seen previously on the previous slides, when you use Q learning, we focus on the action value. When we to work on VA learning, we focus on the state value. So basically, the algorithms in Q learning, it focuses on action selection. Then VA learning, it focuses on state evaluation. Action selection, it's in simple terms, it's policy improvement. Then for VA learning, when we talk about state evaluation, it's basically policy evaluation. To kind of throw more light on policy improvement, it's used in value and policy iteration to evaluate how good a policy is, whether it's improvement or not, whether it's improving or not. That's why we call it policy improvement. Then for policy evaluation, we go ahead and ensure that the agent goes ahead to evaluate the value and the policy, and thus detecting whether the policy is good or not. So the challenges in using both the methods, like we've so far we've seen the methods that Q learning, it's used on small states. Then VA learning, it's used on large states, but then in the end they all have challenges. So one of the challenges which affects both, it's the convergence issues. To kind of break down this convergence issue, remember, for Q learning, it's slow and unstable. That's already an issue concerning convergence. Then for VA learning, it also has slow convergence in policy evaluation. Remember, we've been talking about policy evaluation. So it's also generally slow in policy evaluation. Thus, convergence issues in both instances. Then computational resource requirements. So computational resource requirements, we basically mean that in both methods, they really require high computational resource requirements, thus the high cost. Yeah, like the computational cost is really high. That's making it a challenge of high computational resource requirements in both instances. That's Q learning and VA learning. So to say something on enhancements and hybrid approaches, we have deep Q neural networks that these basically improve Q learning. Yeah, they're also a concept in reinforcement learning, so they basically improve on Q learning. Then if we go ahead and combine VA learning with policy-based methods. This also basically improves on both approaches. That's the Q-learning and yeah. To continue with enhancements and hybrid approaches, we have what we call deep Q neural networks. This it's also a concept in reinforcement learning, whereby for it basically goes ahead to improve on Q learning. Then combining VA learning with policy-based methods, it basically improves on convergence issues. Remember, we looked about the challenges, and one of the challenges was convergence issues. So combining VA learning with policy-based methods goes ahead and improves on the convergence issues, thus improving on the learning efficiency. Then to conclude, last but not least, the future directions, like what we expect in the future in regards to Q learning and future learning. Combining Q learning and VA learning for hybrid models, yeah, just like we've talked about it in the enhancements. Then improving efficiency with transfer learning, applications in robotics and real-time decision making. Then to conclude on some references that we used to go ahead and have this kind of PowerPoint presentation, look at the DQN and PPA. Then the A2C, that's basically a cooperative study that analyzes performance trade-offs in reinforcement learning models for game-based learning. Then the deep double Q learning for actor-centric models, which introduces new bias exploiting algorithms for continuous control. Yeah, that's my presentation.